Some of you can go this side now. Okay. Okay. See, so today, well, I am going to talk about. Well, we are discussing PMM tests, right? So yesterday we talked about all right. These are all part of dynamic tests. Now I will repeat little bit of this y in y out part. It seems there is a little confusion. Let's look at this pure sway test. What has happened here, see, is that the body has been made to sway, oscillate like that. Okay. So the body has been made to oscillate in a pure sway mode. Now the confusion that maybe there is with respect to y in, y out and the forces. So I will just clarify that before going to the next one of pure yaw test. Now let me look at it little more carefully. We will look at it here. Let me take this off. This just some pages have come here. See, I will just look at the maths part of it. Okay. Now I had y given by a0 cos omega t. Okay. So v which is given by y dot will be given by minus omega a0 sin omega t. Okay. V dot will be given by okay. Now I found out a force, y force. I measured the y force, all right. That is what I measured. That means if I have this body here, remember this is my direction y, y dot equal to v, y dot equal to v dot and y force, and of course also n would be n and y are similar, this measured. Right. Now this y that we have measured will be sinusoidal, in some form of sinusoidal. So let me call this to be, this will look like something like y, let us say cos minus beta, or I can call it to be say y1 I can call it this way, because any this force can be like that. You can always check that, no, this is y0 cos omega t cos beta plus y0 sin omega t sin beta. That means in fact you can say that y1 is nothing but y0 cos beta, and y1 is going to be minus sin. This is okay. So this is what we are calling, actually we are calling this one y1 as y in force, because it is in phase with this, with a minus sign of course. If I want to give it a, if you take a mod y, see here, now look at, now we keep this and I just draw this the sinusoidal oscillation, then you will see. First of all y is a cos curve. So if I were to draw here, y is a cos curve, let me put it here for simplicity, this side y, it easier for all of us to understand. So it's a cos curve, means it goes like that. Let me put some 1 2 3 4. Okay. This is my y. What is y dot? Is a minus sign curve. Okay, minus sign curve. The sign would have been this, so minus sign would be something like that. Let us put another pen. Okay, this is my, see here, V equal to y dot minus sin curve with an amplitude omega is 0. Forget the amplitude part. Now we are looking at the phase part. What is V dot? Minus cos curve. So V dot is going to be, let's put minus cos curve, means opposite of that. So it's going to be okay. This we agree. There is no doubt on that. The question comes to the force part. Now I have got to measure the force, so I have no choice on the force part. So what has happened? The force might look, now here there comes the question of color. I don't know which color to use. Let's use the blue color. Let's say the force has come to be, wait, something like that. It has a phase gap. This is my force. Now this I can write, as I showed you, one as a part of a cos curve, one as a part of a sine curve. That means this blue line, this dark blue line can be written to be part of two. One is essentially, you can say, in phase with that, that is this blue line is part of this one and a part of see here. Now I will tell you this blue line okay. Once again you see this is my measurement of y force, that is y cos b something with a phase gap, which is nothing but y1 cos omega t, y2 sin omega t, etc., with a minus sign. So that means this blue line can be written as if it is this small blue line. Actually this small blue line will start from here. In fact this should start from here, whatever, because this 2 was 0, it should have started from here. Let's never mind that. This blue line is sum of this dotted line plus this line. That means I can break this into these two parts. Now you see, if you look at this now dotted blue line, the dotted blue line is in phase with the v dot line, which is out of phase with the displacement. So in other words, the one that is in phase with acceleration, that part, that is a dotted, where is the acceleration? Acceleration is here v dot. Okay, this one. Yeah, okay. Dotted blue line. The dotted blue line here is actually in phase with v dot, right? See, v dot is this, the red line. Red line is a v dot acceleration line. Red line is the acceleration line, and dotted blue line is in phase with the acceleration line, whereas the dotted black line is in phase with the this light blue line, which is velocity line. So that means this is So, I am calling this to be y in and this to be y out. This is what is being called. In other words, what is happening is that you are calling the cos part, this part, this is a question of calling. You need not call in and out, you can call y1, y2, does not matter. Okay, so now once again this is you understand this part. See here, I have a displacement, I have a velocity, I have an acceleration. If I were to do once more this in only a simpler one, just with the velocity acceleration, let me put that in a better way of use the velocity acceleration. What will happen is that I just take the velocity acceleration here. See here, velocity was this line. See, my velocity became this line. This is v, agreed. My acceleration is the red line, that is okay. My force is some line here. Now, this particular force, I actually, let me show the braking part and then I can show this. The force turns out to be equal to plus or if you sum this up, then of course the force value is here. Let me put it this way. Here the force value is supposed to be this two line somewhere here. So, the force value may look something like that. See, this is the now come again we will go very carefully on this part. See here, this v dot, okay, this v, black one is y force, black one is equal to y in plus y out. What is y in? So, what is happening once again, this black line is the force that I measured, okay, but this black line is this one, y0 cos omega t minus beta, but this, as you know, you can write this as y1 cos omega t plus y2 sin omega t. That means, this black line is a cos omega t curve, and this is actually okay, this one, and a sin omega t curve. Okay. See, this is a cos omega t curve, and this is a sin omega t curve. This sum, this two dotted line sum, gave me the black line, or conversely the back line is what I have got, can be written broken down to this two. So, I am only calling one of them as in phase, one of them out of phase, that is it. That means, one component which is actually, see, whether you call y1, y2, y in, y out does not make a difference. The main point is that there is a part of the force that is what we can call in phase with acceleration or displacement, and the other one is out of phase with acceleration or in phase with velocity. That is all. Okay. So, this is what we are calling this way. We will actually see this later on. I thought I will towards the end show the entire thing in a little more equation form to see how this thing work out. But let us now go out to my the other point today, what we are talking of, pure yaw test. In this case, what we need to do? I want to make sure the model moves always tangential to this. Let me just draw this. Okay. So, what I need, remember, I need to make sure that the model moves like that, because that way what would happen if you look at any point here, see here I have got here V. So, this side, so not sorry, that is U, let me call it big U only, or U bar. This side V is 0. Okay. That means it is only rotating. So, there is no V, but there is only rotation, because after all you are just rotating in this way. That is the idea. How do I achieve that? Question number 1, how do I achieve that? Okay. Now, let me just blow up one part. Let me take this part and blow it up and see what is the way of doing this. So, let us look at this part, just one part. Okay. So, where I did is this way, model is here. Now, you see here so, I have here y, yesterday we called it, okay, let me call it bow or forward. Okay. Say this is A0, then y aft. Omega t minus epsilon. There is a phase gap you have to keep. Okay. See here, we will go carefully. Okay. See what is happening, I have to make sure that my velocity vector v is tangential to the path line, right. That is a requirement. Look at this here, I have to always orient a body, that is the velocity vector must be tangential to the path line. That is a requirement. So, it is very simple, I will be actually asking you to derive this formula, but I will tell you the clue by which it should be done. The question is that, see what is happening here. Now, what is the velocity here? This velocity here is given by v as y dot d by dt of half y a plus y b. Agreed? This is my v. What is this psi? Now, you should now remember this is v and this is u. Actually, this psi is always small angle. So, u and v equal to close by, although this diagram shows very exaggerated one. Now, what is happening, see here, v is equal to, or v by u equal to, let me call it here tan psi. Of course, it can be also become equal to psi if psi is small, which is what we will be taking. Okay. This you agree, because you see here, this you take a velocity vector here, obviously v by u, if you draw this diagram here, this is v, this is u, this u. So, this psi, we are calling this to be psi. So, that relation holds good, that is one. All right. Now, the other question is that V is equal to, now here V is this, V is actually d by dt of y dot, that is d by dt of half of d by dt of y a dot plus y b dot. So, it will involve omega epsilon here. In other words, what is happening here, that if I were to, let me go to the other one, see V is 0.5 y a dot plus 0.5 y b dot. Okay. So, this if I were to do y a dot y b dot, see y a dot is what, minus a 0 cos omega t minus epsilon minus omega a 0 cos omega t minus epsilon, that means 0.5. I am just writing this just for the sake of writing, no, plus it, plus omega a 0 cos omega t minus, well, this is b actually, epsilon plus 0.5, essentially like that. Okay. So, in other words, now what will I have, V equal to u tan psi. So, V for psi small, or rather we will write that way, psi equal to V by u. Okay. This is one, this is a relation 1, which is what I am writing, but there is a relation 2 there. What is psi? Psi is given by y b minus y a divided by this angle. See, psi is also y b minus y a divided by this distance, because this is small, anyhow this distance is small, we are taking this psi to be small. If you want, you can always do this by like this is this way, sin psi, cos psi, this by this is cos after all, right. So, but we are taking small psi. So, what is happening for small psi, once again the psi is also y b minus y a by 2 x x, that is 2. So, when 1 equal to 2 will give you epsilon as function of omega u essentially omega and x x. This equation I will want you to solve, but if you solve it, the answer that will come out to be, which is what I am just writing here, by solving you will end up getting that, or I will write it next line, next page, you will end up getting that we can call it u 0, we are calling this to be actually we are calling it to be u 0. See, once again let me tell you this, what you are doing, see, this is an assignment to you. So, that is why I am trying to tell you this will be an assignment to prove derive that expression. What we are trying to find out is that what is the condition or necessary, that is what must be the value of epsilon, so that the path line is or the velocity vector v is tangential to the path line. This is the requirement. V must be tangential to the path line. Remember, here I have a path line here, say I have a path line here, my velocity vector must be always tangential to this. This is my requirement. So, the question I have asked myself is, what is that epsilon I should keep, what is the signal I should keep, what is the phase gap I should keep. See, here you can see from here the phase gap. What I am doing is that I want to make this phase in such a way that it always goes like that. See, this phase, this two line I am opposing in such a way that it is always tangential to that. This will be only achieved by keeping a certain value of epsilon? How do I derive it? That is what the one I was trying to tell. The condition is very simple, that this epsilon angle is this minus that by L. This minus this by this length is epsilon for small value of epsilon. Similarly, now that is one. Also epsilon is given by V by U, right, because tan epsilon is V by U, tan epsilon is epsilon because angle is small. But what is V? V is U dot, Y dot. Y dot is half Y A plus Y B, d by dt of that. So here I have got epsilon coming. There also I have got epsilon coming. That means this equation that I was trying to tell, in this I have got epsilon coming. In this also I have epsilon coming because this is epsilon here, all in term of cos. So I equate this with that. Then I will have an expression, the only unknown being epsilon. So I will know what is the value of epsilon. That means the question I have asked is, what is the value of epsilon for which 2 is equal to 1? This you solve it, and if you solve it, the answer that comes out, that is what I said here, is given as cos inverse of this or cos epsilon is this. This is I am leaving that to you for the class to derive, because it is a simple, it is basically an algebra. So when you carry out the algebra, you will be able to find it out. Now what happened? Actually this is a very simple case, people could work it out, this algebra, for much complex case of an arbitrary body of y a y b. In other words, what is this y a? Arbitrary body of y a y b. Supposing I give a1 here, a2 here, this distance is also not x x etc. In that case also you can find out a general expression. Essentially all I am looking is at what is the expression, so that this becomes tangential. Obviously they will depend on u, it will depend on the frequency of oscillation, and it will depend on the distance, this two distance. So here result comes out to be this. Okay. So now having said that, what happened? Now we come back to this expression again. So here we end up getting this. Therefore if that epsilon is there, I will just draw it again. Body is etc. So here I end up getting here this path line turns out to be y in this diagram. I am just showing because this is my plus y. Okay. Oh, sorry. And this is my, this of course this is the maximum value psi, but generally speaking psi, just the heading angle psi with the minus sign here. You will find out that this expression will come out, that psi will obviously become a sign. See, having done this expression, I can now find out psi. Psi is nothing but y2 minus y1 by 2x. 2x comes in, and if you do that, it will turn out that obviously it will be a sinusoidal function. In this case, it will turn out to be minus y0 cos omega t minus epsilon by 2. In other words, if I keep a phase gap epsilon given by the expression this, then it turns out, which is also what you should derive, that first of all the fact that epsilon must be so and so, in order to make sure my path line and velocity vector are tangential, or velocity vector is tangential to path line, that will give you by this expression. and if you put this expression, you will end up getting psi to be given by this. Now, this is very simple. Now, what has happened? See, I have got a heading angle psi given by a sinusoidal function. So, what I end up getting this equal to minus psi 0 . Now, the rest part is very simple. Then psi dot equal to r equal to plus psi 0 omega exactly same as what we have done before. That means, I have a heading angle given by a curve cos curve. Okay, the heading angle, if I were to plot heading angle, rotational velocity sine curve, rotational acceleration as cos curve, just like what we have done before. In other words, if I were to draw the psi curve and all, let me put it here again. Psi is a minus cos curve. So, if I see this side plus, okay, or rather I call this plus here, this time this side plus psi I will put it. So, minus cos curves will look like this is psi curve, okay, with a gap there. I am just putting this epsilon 0, just choosing the value from somewhere. R is going to be therefore plus sine curve. R is plus sine curve, that is this is plus side, okay. See here, r dot equal to plus cos curve, and similarly you are going to get the force, okay. Exactly same way. Now, I do not have to go further beyond that. You are going to measure a force, some force will come, something like that. Again you have this plus and minus part. So, you are going to find out here again y force, which will be y 0 cos maybe minus a beta. Here we write other way around. See, cos was this thing, yeah, okay, y. So, the procedure becomes same. I do not have to actually go through the procedure anymore. The procedure is exactly same. You are measuring the y force, n moment. In case 1, I had only y, that is only v, no r, and v was a sinusoidal curve. Now, I have only r, no v. R is a sinusoidal curve. So, the the end of story in a sense, because it is exactly same. So, of course, here when you want to use the equations, then it will turn out therefore, this thing y r minus m u 0 will turn out to be y b. If you rate y b out and y s out, there is both ones turn out. I will tell you why. This there is no, see, these terms come because of the, see, when you, I will tell you about this term, let me write it down this. We are writing plus minus etc., just so that you make the appropriate this will be actually minus probably, this will be minus here. oh sorry, and n r dot minus I this is not in, this will be again a mistake here. Okay, okay, this is out, this is in here, this is in. See, the thing is that these terms are coming. See, this part is okay, you know. The problem the question is very simple. Once again, same procedure. This for this value, this is the yb out, nb out, etc. What we have done before. The only thing that you might doubt where these expressions come, this side expression come. That is because remember, whenever I measure a force, I always measure the forces which includes the mass inertia. For example, if I took a body and I oscillated that in water, I will end up getting mass plus added mass into acceleration force. I will not find out only added mass in acceleration. See, if I took a body, for example, in water and I accelerate that, my equipment will measure mass plus added mass into acceleration, that force, not only added mass into acceleration force. So, the measurement of yb out, etc. includes these parts, that is C m u 0 into velocity, m x g u 0 into velocity, m x g into acceleration, y z into acceleration. Say for example, this one is very easy, I z into acceleration, this is my inertia force. So, that is why this term has to be taken into consideration always, because remember, in other words, what you should do, if you do not want it, take yb out total measure minus this part will give you the yb out for hydrodynamics only. It is the same thing. I could take this minus this much and then divide by that part again, it is the same thing. In other words, what I am saying is that just think of this, the measurement, the measured force, say y, will include always, say you know, like just give an example, yv v dot plus m v dot, this part also is included. So, if you don't, if you want only this much, what you could do, you can do m v dot and define this to be y hydrodynamics, and then take y hydro divided by v dot to get y v dot. Okay. Same thing where I am just trying to explain to you what I am saying is that the measurement forces will always include this. As a result, if I want to find out hydrodynamic, this is in a body inertia force, hydrodynamic force, measured forces always includes body inertia forces. So, if I want to determine hydrodynamic forces, first of all I should take this off from here and then divide by v dot to find out the derivative. That means, this would be my hydrodynamic force, and therefore, y v dot is y hydro by v dot. Okay. That is what we have done. These are nothing but the v dots here. So, m, this inertia force, that is this into this part inertia force, had to be taken out, or you can write this way, whichever way you can. In other words, what I mean, here I can write, basically I can write this v dot here, say in this expression I can write v dot to be y minus m divided by v dot, what we have written here, sorry, not v dot, y v, y v dot equal to y minus, no sorry, no, I made a mistake. What I can do is here, see here, this y by v dot equal to y v dot plus m. This is what we are getting, no, this expression. See here, y by v dot is y v dot plus m. This is exactly what we have done. This minus that is this by this. Exactly, that is what we are getting here, this expression. So, it is the same thing. I just wanted to tell you this part. Okay. So, this is how we are doing our you know, like this rotating PMM technique, etc. I just want to tell you here quickly, I do not know if I have time, maybe I should quickly go through that. There is a nicer way of doing this entire thing, in a more maths way to show all these parts, you know. I will very quickly try to go through this. It's going to be all kind of equation. See, here what I want to do, we have shown this separately, saying that I can do pure sway, pure y, pure sway, pure yaw by taking this phase, etc., etc. But you know, the entire thing can come out in an equation form if I play with the equation of motion with this. For example, see here I have these two struts, y a aft strut was given by a cos omega t. Let us see this aft strut motion. Forward strut motion is given as b. I am just writing a general expression, b cos omega t plus psi, some phase gap there. I am measuring forces aft, it is coming out to be say f a cos omega t plus theta a. Forward will turn out to be f b okay. Now, what I said here, this is an input data I gave, okay. This strut y a y b, measured forces y a y b. This is measurement of forces, this is the input data I am giving, which what I have determined, I have given input a, b, psi are input data, I have given this. What I measured, f a theta a theta b, f a f b theta a theta b, that is what I measured, right. This is exactly what I have done in an equation. Now, if the equation of motion is like that, linear equation of motion was given by y v dot minus y v v plus a. I just writing very quickly because time, you can always work it out. This is my external force, this net force is y a y b, that is what I measured. Similarly, here I z minus into L, we are calling this to be L. This net moment, this I am calling this to be L, the distance. Now, V equal to y a dot plus y b dot by 2 and R equal to y b dot minus y a dot by 2 L. I will leave it to you to work it out. You see this part very simple, psi equal to y b by y a minus 2 L. So, R dot is R equal to psi dot, remember psi equal to y b minus y a by 2, this is actually no, this 2 L comes in because this is actually 2 L here, sorry, this into this. Okay, that is okay, this is 2 L, this is 2 L. This is the moment is y b minus y b into L plus, yeah, okay, because this is y b L y a L. So, this is this by 2 L. So, R equal to psi dot, R equal to psi dot, that gives you this expression. Okay. We now what happened, if you make the distances a equal to b, that y a equal to y, that basically a equal to b, if you make this same, if remember a equal to b basically means a and b, this the amplitude of these two motions are same, then what we end up getting is like that. I want to just show you very quickly, you can work it out yourself. and r dot turns out to be minus a omega square by 2 L cos psi minus 1 minus sin omega t sin psi. Now, here basically if you equate from v dot this thing sin and cos term both sides, okay, then we will what is meant by that. See, we know this v, remember v is given by this plus that by 2, r is this by that by 2. So, v, if I put this expression, there will be sin and cos term, because this is cos a cos b sin a sin b. Okay. Similarly, r will have sin and cos term. So, now what is happening, this side has sin and cos, this side sin. When I equate the sin and cos terms, then I end up getting 4 equations. Why I am telling you is that let us first equate these 4 terms. Maybe I will ask you to do the entire part. I will just show you one equation, but you can do the rest part. This will become equal to f a cos theta a plus f b cos theta b. And what we are doing, I will tell you once again. Let us see here. Anyway, see here. I know this v dot r dot. Okay, these are having sin and cos terms, right? I put this expression here. Okay, on this. What will happen this side? I have sin and cos terms. Here y a plus y b also has sin and cos terms, because cos omega t plus theta etc. So, now this side and that side. So, I equate sin with sin, cos with cos. If you do that, you end up getting actually 4 expression here, that you basically end up getting 4 expression independent. You end up getting 4 independent equation. This is one of the one that I showed you just now. This is one. Like that you will get 4 equation. Okay. The interesting point is that this 4 equation, after you get, I will not go through the 4 equation, but you do this 4 equation, then you will see that if you put psi equal to 0, okay, remarkably you get 4 equations. Actually, here you are going to get 4 equations with unknown of yv dot yr dot nv dot nr dot. You will end up getting like this 4 equations with 8 unknowns. Those unknowns are the one, these 8 unknowns. Okay. But now the most interesting part comes out. This is, I will leave it to you for exercise. Now you make psi equal to 0, you will end up getting 4 reduced equation with only these 4 unknowns. For example, you will end up getting, I will just give you one example, yv dot people have come already or what? and last one. See here, you will get this 4 equation with the unknowns, this 4, this one, this one, this one, this one. So what is happening? You see here the interesting point therefore. So when I make psi equal to 0, that I of course I can always make psi equal to 0, because here you see this psi. If I make psi equal to 0 here, okay, then I will end up getting 4 equations with 4 unknowns. Therefore, for when I do the experiment with psi equal to 0, that becomes a pure sway test. You have the 4 equations, I can solve it. I am measuring Fa, Fb, theta A, theta B, 4 unknowns I am measuring, remember. So I have measured this, I have inputted, basically what did I input? I input psi, of course this case psi was 0, but I have omega, I have L, I have U 0. This is given values. So for a given value of this with psi 0, I end up getting, I measured Fa and theta A, 4 unknowns, and the 4 equations I can solve for the 4 unknowns. Same way if you make psi equal to 180 degree, okay, you will end up getting just or the other 4 equations where I will have only y r dot etc etc. That means similar way if I make psi equal to 180 degree. So if 4 equation will emerge. You can solve it. Okay. So what is happening therefore, see why I wanted to show you, this tells me an interesting way. Supposing I don't keep psi equal to even 0, see I can, the why I am showing that, you don't make it pure sway, you don't make it pure heave. I can make psi equal to 45 degree, I get 4 equations with 8 unknowns. I take psi equal to another angle, say 90, say 135 degree or whatever, I get another 4 equation with 8 unknowns. So I will get total 8 equation with 8 unknowns, I can solve for it. So why I am saying, therefore PMM as a technique can be generalized. You need not give necessarily psi equal to 0 and 180 or pure sway pure yaw, although that is what is done. I can also have sway yaw mixed, make 2 experiments and separate it out. You see the hints are tantalizing. In other words, if you have the capacity to go through the maths rigor, you will find out that you can also determine the nonlinear coefficients by simply taking this playing around. That is why I want to show you this. If you go by equation of motion, and you can generalize it in a much more complex way. Although conventionally we would normally do pure sway and pure yaw, and this is what we do. I will just want to tell you at the very end that for submarines what happens, you also want to know, like if you look at my this thing, this is my horizontal plane motions, but in submarine you also want to know vertical plate. So what they do in a submarine, the planar motion mechanism actually is vertical, submarine is model is kept like that, where I can oscillate it this way. So I can oscillate it vertical plane, this is my z, okay, this is my x. But the same one, what I should do is that suppose the body is kept this way, this is very interesting, in a submerged body I keep it this way, I oscillate, but if I want yv and all I do is this way and oscillate it. I just rotate the model 90 degree and oscillate, so I can get horizontal plane motion, because in deep water I can simply make this as horizontal plane by making the body like that. So you see VPMM, what is called for submarine, where it is submerged, I can actually oscillate in a vertical mode, but this vertical direction can be made the x direction, y direction, by simply turning the model upside down. So you can get both yv etc. and also zw etc. That is what is called vertical planar motion mechanism applied for submerged bodies, whereas for surface bodies we use horizontal planar motion mechanism, because my free surface has to be there. It has to be half submerged, you cannot deeply submerge it. So this is about planar motion mechanism. I will end it here, and we will see from next class we will probably go to control surface design and control radar part. So, this but as I said, this derivation of this phase angle that I mentioned earlier, kindly do that as an exercise to see that this expression comes out, gives you a good feel, and if you have the tenacity you can generalize that for any value of a and b, ya, yb and etc., unsymmetrical part. Then you will find you have a much more complex expression. Nevertheless, an expression is possible. Okay, with that I will end it here.